Hey, we're going to break down the atom as one of the first things that we talk about in chemistry. And we want to break down the atom so that we know what the little parts are called and things like that. Throughout the next couple of months when we talk about chemistry and we talk about this guy mixing with this guy and making a new compound or something like that, you got to know why that's allowed to happen, okay? Why does this element here want to be attracted to this element over here? And so we're going to break down little parts of the atom, and those are called subatomic particles. And that's what we'll cover here just real quick. All right, it's been a little while since you've watched one of these, so pause it along the way and take down the few notes that you'll have, okay? So get down a title, and then we'll go on. All right. You're going to have two distinct regions to any atom, okay? It could be a really complex atom made up of tons and tons of protons and electrons, something at the bottom of the periodic table, okay? Something like plutonium or gold. They've got lots and lots of protons and pieces to it, okay? It can be really simple, though. It can have one proton and one electron. It can be real simple, like a hydrogen atom, okay? But there's two regions, all right? There's a central region, just like in cells, which we used to call the nucleus, all right? Back to biology. Well, here in chemistry, you're going to have also a nucleus, okay? And it's the central portion of the atom, all right? It's made up of those guys there, the proton and the neutron, okay? And you don't have to make one with so many little spheres, but if you would, just kind of sketch real quick, protons and neutrons held together, okay? And so that's one region of any atom, all right? One thing you should probably toss in there with your protons, if you're not using separate colors, put a plus in some of those, okay? They have positive charges, and so that's what those pluses are all about, just like magnets almost, all right? And they have magnetic attractions to certain things, okay? So you got your nucleus, and then outside of that, we've got what's called an electron cloud, all right? Years ago, it wasn't thought to be a cloud, but it's been recently shown that electrons don't move like planets around the nucleus. That's what it used to, the model of an atom used to be like. It used to be that central portion, that nucleus, and then almost just little electrons zooming around in orbit in all different directions. It's kind of how we tend to think of the atom. And I'm going to just real quick, you know, anytime you look up an atom, you know, most of your images are going to be that way. But it's wrong, okay? They don't move around in perfect little circles like that, okay? They don't move around in what we call orbits. So back to here. The electrons are just found outside of that nucleus in what's called an electron cloud. So there's your two regions, okay? All right. I said that the parts of an atom are called subatomic particles. I've already been using the names proton, neutron, and electron. All right, and when I say sub, it just means smaller than an atom, okay? So just a few notes about each one, and then that's pretty much it, okay? Protons have a positive charge, we said that, all right? The proton's important though, okay? The number of protons identifies the element. All right, I'll say that again. Let's go to a picture of a periodic table. Okay, the number of protons identifies the element. All right, carbon right here. See that 6? That's the atomic number. It has 6 protons. If you could somehow get on a small little scale and strip away a proton, you're no longer carbon. All right, you're going to have different properties. You're going to have properties that of boron. Okay. If you're oxygen and you have 8 protons, and you could somehow take 2 protons away from it, you're going to turn it into a carbon atom. All right. Well, this is a solid, and oxygen's a gas, and so you've completely changed the makeup, but just by removing or adding protons. Okay. So protons identify the element. All right. If I said which element has 1 proton, all you have to do is go up here and find the one that's got a number 1 next to it. Okay. I said which one has 79 protons in its nucleus. Boom. You just go down here. You go, oh, it's gold. Okay. We'll talk about symbols and names later. All right. So that's protons. All right. They identify the element. It's called the atomic number. They're the same thing. Carbon has an atomic number of 6. It has 6 protons. Back to here. Carbon has 6 up here. It's the atomic number. 6 protons. Okay? Pretty simple. All right. Now, recently, and I say recently within the last maybe 50 years or so, maybe even sooner than that, but they found out that protons can even be broken down. As time goes on, we keep finding that we can go smaller. Okay, so it used to be the atom had to be the smallest thing that there could ever be. All right, and then they said, hold on, well the atom's made up of something. It's made up of protons and neutrons and electrons. All right, well then there must be nothing smaller than that. And then it came out that, hold on a second, you can take a proton and you can break it apart, and it breaks up into these little things called quarks. All right, and so I'm asking you to write down that protons can be made up of things called quarks. Okay, so there's the proton. The next subatomic particle, and if you want to pause it, go for it. The next one is the neutron, all right, and it's the second thing that makes up the nucleus. Okay, it just so happens it has no charge. All right, proton was a positive charge. These guys have no charge. All right, their mass, as small as it is, right, you can't hold one of these things. They're extremely small, on the order of magnitude of like 10 to the negative 24th or something crazy like that. We're talking super duper small. That being said, neutrons have about the same mass as a proton. Okay. We say that neutrons determine the isotope of an atom, and what I mean by that is most elements have different versions of themselves. Okay, so I'm just going to go ahead and pick on carbon here. All right, carbon has 6 protons, no matter what. It's always going to have that. Okay, but in its nucleus, you can have more than 6 neutrons. Okay, you can have 6, and it's the most common type of carbon. But you can also have 7 neutrons or even 8. And that bumps up what we call its atomic mass. Okay? And so when I write C12, C13, C14, that's the mass of that specific atom that you might be able to hold in your hand. Okay? Myself, I'm made up of C12 and C14. All living things are made up of carbon, and both versions. Okay? But as you die, when you die, these C14s here, they actually start to change. They're radioactive, and they don't stay that way. And as time goes on, those C14s disappear, and you end up being left with only C12s, because C12s are really stable. They're fine the way they are. But those extra neutrons on that C14, they don't like to be in that fashion, and as time goes on, they strip away. This whole idea is what's behind what's called radiocarbon dating, or if you want to date fossils, all right, you go get a dinosaur bone that you found out in the middle of the Montana whatever, and you dug out a dinosaur bone, you can see how much C14 it still has, all right, because as it changes, scientists know how long it takes for C14 to disappear, and they can tell you how old that bone is according to the types of carbon left in it, all right. So just know this, neutrons, you're not sure at any given time, if I just gave you a million a million carbon atoms, you're not sure to pick up one that has 6 and 6. 6 protons, 6 neutrons. You might have some with more neutrons, all right? That's what you got to know about that. Those are called isotopes. Okay? Pause it, jot it down. And then finally, just the electron, okay? I write down the terms no mass relative to the nucleus, and all I mean by that is even on how small these things are, the electron is even smaller. It's extremely small, even on that level, okay? Really tiny, all right? They surround that nucleus in that space called that electron cloud, okay? And they have a negative charge, and we've been taught all along that opposites attract, so that's why electrons like to hang around with protons. They're oppositely attracted, so that's why they're attracted, okay? If you've got an element that's got 3 protons and an atomic number of 3, it's going to have 3 electrons attached to it. It's got the power to hold on to 3. Can't hold on to 4. It can hold on to more than 2. So 3 protons holds 3 electrons. So those numbers tend to stay the same on any given element. All right. So if we look at a periodic table again, and I gave you an iron atom right here, Fe. Okay. If I gave you an iron atom, it would have 26 protons if you could pick them out. Okay. It might have 26 neutrons, and it would have 26 electrons, because 26 protons can hold on to that many electrons. All right. So that's the subatomic particles. Okay. When we talk about the size of these things, single atoms, we're talking real tiny. Okay. So real quick, just take a look at this. Okay. And I know that my picture might be blocking this, so I'll read it. But it says the atom compared to a penny is the same as a penny compared to the moon. So imagine you walk to the moon and you take a penny and you're standing there, all right? And how big is that penny compared to the moon, right? It's extremely small, okay? That would be the same as if you were to hold an atom up to a single tiny penny, all right? So as far as size is concerned, an atom is as big to a penny as is as big to the moon, okay? So we're talking about, when we say a single atom, extremely, extremely small, even smaller than a single cell, okay? And then one more little comparison about size, and I know part of it's blocked, but this says that matter is mostly empty space. This is Kenan Stadium. This is where the North Carolina Tar Heels play, all right? If that whole stadium was an atom, okay, and you could take a golf ball and put it in the middle, that's how big the nucleus is compared to the entire stadium. The whole stadium is the atom. The electrons have a ton of room to move around, okay? This would be the size of the nucleus. So the nucleus it holds most of the mass, all right? And it's really, really small and compact, and then around it, you've got all kinds of room for electrons to exist, okay? And that's how much room these guys, that's how much space these guys take up, okay? Really tiny things. I'm going to play a YouTube video that's connected to this, and you won't be able to hear it real well, but there's really nothing to hear. It's more to read, okay? So kind of watch this for me.
You're watching a Nova Science Now video podcast. For more fun science stories, watch the new season of Nova Science.
That kind of wraps up what we just said about the size of the particles and how they move and so forth and where they're located. Okay, 2 models and then we're done. All right, the Bohr model. This was that original model. Looks like planets revolving around. Okay, revolving around the nucleus. No longer accepted. Jot that down. Okay, and then finally the electron cloud model. More precise, puts those electrons kind of anywhere within a given space around the nucleus. Okay? Have your notes for tomorrow. Try and work on your timeline and be ready to answer some questions about this, okay? All right.